Transforming quadratics. Again, we spoke about the three. This is the last one. We're talking about vertical stretches and compressions. And what that is are A values. So we're going to talk about what the A value actually does to our quadratics. Okay? So, we're going to go over to our program here. There we go. And in our program, remember we had the x to the power of 2 makes that shape. Our A value is the coefficient, the number in the front of it. So, I'm going to put the number 1 in to start. Was there any change? No. Okay. Now remember, I put values of 0 before, and they didn't change anything. I put 1 this time. If I put 0, it doesn't exist anymore. Okay? So what that means is, on the original one, the A value is actually 1. It's a little different from the H and the K. We're going to get into that. Okay? So, great question. 4 and 5, right? So let's try the value of 4. X squared. What has it done to this parabola? Okay. It's made it thinner. Okay? And the reason we call this a stretch is because we called it a vertical translation. Okay? So a vertical translation, or sorry, not translation, stretch. Think of it like an elastic band. And you're pulling the band from the top. What would happen to the elastic band? It would become stretched. It would be thinner. That's what they mean by a vertical stretch. Anytime we have a value greater than 1, it becomes stretched compared to the original. And the greater that value is, the more stretched it becomes. So let's try a value of 13 maybe. And if you notice, this is even more stretched than our red one, where 4x squared. Okay? So the greater we get above 1, the more stretched the parabola becomes. It becomes much thinner. Now another value, and I didn't mean to talk about this at the beginning. We'll do this one instead. Any value between 0 and 1. So let's say like 0.4 x squared. Okay. This makes it wider than before. They call it compression. The reason they call it vertical compression is, think of it like something heavy is being pushed on top. If it's being pushed on top, it becomes wider, like it's being squished. That's what they mean by a vertical compression.
So is it every time you add a bar, they just give you a random information?
Yeah. Oh, I see one. So, anytime we're between 0 and 1. Now the reason I don't just say less than 1 is because when we go less than 0, and I'm actually going to put the value of negative 1x squared, what do we get? Aha. So when a is a negative value, it actually flips. And what is this essentially a mirror reflection of? This negative 1 is a mirror reflection of the positive 1. Great. So what I'm going to do is I'm going to put up some mirror reflections. Negative 4x squared. Okay? A little hard to see, but if you notice, it's a reflection of our positive 4. It's become thinner even though it's facing downwards. The same idea is going to happen with our 13 if we do negative 13. Where is it? Negative 13 x squared. Okay? Again, it's made it even thinner. All it's doing is the negative value is making it face downwards. Okay? And finally, if we do negative 0.4, will it become wider or thinner? That's right. It's going to become wider and face downwards. Okay? So, between 0 and 1 makes things wider. Greater than 1 makes things thinner. And anything negative makes it face downwards. That's the pattern we've just discovered with our A.